Welcome back to Module 22 of Engineering Vibrations and Introduction to Single Degree of Freedom Systems. Today's learning outcome is to derive the differential equation of motion, or the DEOM, for a simple single degree of freedom SDOF system. This time we're going to introduce damping. And so up until this point, when we solved the systems, we had only used masses and springs, but now I'm going to include those dampers. So here's a video of a damped system. This is a golf cart, and you can see the motion up and down with the suspension system. I went ahead and took a picture underneath the golf cart so you could see the suspension system. You can see that the springing action comes from a leaf spring, and the damping, which we call a shock absorber, is shown there as well. The interesting thing is a shock absorber really doesn't absorb the shock. The spring absorbs the shock. The shock absorber that's there dissipates the energy and is a function relative, or it's proportional to the velocity. And so it's really a damper. As far as the spring is concerned, with a leaf spring, it's very close to this model where we have a beam, your force is in the center, and the springing action, the equivalent spring for that beam or leaf spring, is given by some sort of a formula. It may not be exactly PL cubed over 48 EI in this case, but it's the same sort of a process. And so here is my model. Let's say this is a quarter of the golf cart model. So the mass is just the one back corner that I was looking at. And the springing and the damping action is for the suspension system in that back corner. I've chosen my generalized coordinate as Y, and I'm going to give it some initial conditions of an initial displacement upward and an initial velocity downward. Obviously, when I videoed, I was giving it in the opposite direction, but you can give the initial displacements any way is physically represented. Okay, so do a free body diagram equals kinetic diagram. I draw the system in its displaced position, so I'm going to have the displacement up along with the velocity and acceleration up. So that's going to give me a spring force from the static equilibrium position down, Ky, and the damping force will be Cy dot. On my kinetic diagram, I'm going to have my mass times my acceleration in the positive direction upward. Once I have that good free body diagram equals kinetic diagram, I can come up with my equation of motion. I'm going to go ahead and sum forces in the y direction. When I do so, this is the equation that I get, and I can rearrange it for my double dot plus cy dot plus ky equals 0. And this is the differential equation of motion for that system. And I've also given you a system for you to come up with a differential equation of motion. This is a rotational system. You should be able to do it based on our modules so far where we looked at rotational systems. And you can check your solution with the solution that I've added to the module. So that's it for today's module. The summary is that we derived a differential equation for a simple single degree of freedom oscillator or system undergoing free damp vibration, plus I gave you a worksheet to do on your own. And with that, I'll see you next time.